So keep in mind that what we are going to try to prove is that, in fact, f of alpha defined in this way is a function with this property. And that property will follow pretty easily from the fact that once we've shown it's a function, we'll know that it has, its terms defined by this sequence. It'll be easy enough to demonstrate what's written in red once we know that X satisfies the formula starting with the orange existential claim. So, we will prove that this holds by induction on alpha. So if alpha is, in here, let me say what the sequence is that satisfies the existential claim in each case. Well, it will be different if alpha is a limit ordinal or a successor ordinal. So if it is a limit ordinal, we define it in this way: the union of all things leading up to alpha. And in the case where alpha is equal to 0, then this is just the empty union and therefore the empty set, and things will actually work out exactly as they should in that case. So I don't really have to make a, basically this is just a little trivial trick so that I don't have to have a separate case for when alpha is equal to 0. But in any case, when alpha is a successor ordinal equal to beta plus 1, and assuming that, right, this is how proof by induction goes, you assume that the previous ordinal satisfies the claim, then we define, that entails the existence of some sequence, and we define our sequence to satisfy the existential claim as being the same sequence up to alpha, but then for alpha, we, define that, the next term, basically, for when we pick beta to be the upper limit or something like that. So anyway, that's how we get the a sub alpha term. So now we will show that the sequence so defined will satisfy the existential claim. And also what we need to do is show that the function is well defined, right? So that this formula determines one and only one value of X. That's an important part of what we will show. So, as I said, for the case where the function, where the ordinal alpha is 0 or the empty set, then the claim holds trivially. Alpha is the empty set, F restricted to alpha is the empty set, and G, being defined on V, the universe of sets, is defined for the empty set, and so everything works out fairly trivially. Now, where alpha is a successor ordinal, I kind of skip the demonstration that it satisfies that this particular sequence so defined earlier satisfies the for all sentence written in brown earlier. In order to show, we still need to show that X is uniquely determined and that, f of alpha equals G restricted to G of F restricted to alpha. And since F of alpha is just equal to X, and X is equal to this, then it really just amounts to showing this equality. Now, to show that X is uniquely determined, we could just show, right, because G is a function, and therefore, for any unique input, you get a unique output. Well, we could just show that the sequences are uniquely determined, and that can be done by induction. I think the proof by induction is fairly simple, so I skip it. And then the proof that this equation holds is pretty much just by definition. It's pretty straightforward, just due to the fact that the restriction of F is to alpha. Since we know everything up to alpha in this case, then the restriction of F up to alpha is just equal to that sequence.